Alright, so today we are looking at differential equations. Again, this is the second one. We're looking at general and particular solutions. General solutions have plus c. Particular solutions use an initial condition to plug it in, and then you'll get an actual function, not a family of functions. Homogeneous, defining homogeneous and what that means. Logistic growth functions, and some applications that are some word problems. So let's get started. So finding the general solution, we just anti-differentiate. That's all we do. So we just, you can say, okay, dy equals secant squared x plus 2x plus 5, and then have the dx. See, this dx just came over here. So we're essentially separating our variables, and then integrate. So we have y equals integral secant squared is tangent. Integral of 2x is x squared, and we have 5x plus c. We're combining the plus c's from the left and the right. How about this? Well, we're looking at something, and it looks like we can separate it. So let's separate the variables. So we have 3y dy dx equals negative x squared. Dy can come over here, so we have 3y dy equals negative x squared dx. And then solve. We got 3 halves y squared equals negative x cubed over 3 plus c. And, I mean, you could, do some more. So let's do some more to get y, a little bit more on its own. So we can multiply by 2/3, multiply by 2/3, pew 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 pew. Y squared equals negative 2x cubed over 9 plus c. It's a different c, but it's still c. And then, you can do y equals plus or minus, and then square root of this stuff if you want. 9 plus c. Cool. What about a particular solution? Particular solution, you find the general solution, plug in your initial condition, and then there you go. That's the particular solution. So let's try it. So we got, well, we can separate our variables, right? Because this can come to the left, and x can come to the right. So we have dy over e to the 2y equals x minus 2 dx. Okay. That's kind of gross, but that's okay. Maybe we'll make this into a negative exponent instead of a reciprocal. So we got, this is x minus 2 dx. So now we can do that, and we have chain rule, so e to the negative 2y divided by negative 2, because the chain rule is going to multiply by negative 2, so we got to divide by that, equals x squared over 2 minus 2x plus c. And now here we need to think, okay, how do I figure out what c is? Well, we should probably work on getting y. And then we can handle it. So maybe what exponent rules could we do? Well, we could natural log both sides after we get rid of this negative 1/2. So we do e to the negative 2y equals, because I'm multiplying by negative 2, multiply by negative 2. So pew, pew, those cancel. And we have negative x squared plus 4x plus c. Okay. And now we can natural log both sides. We got negative 2y equals natural log of, well, we gotta make sure that inside the natural log is positive, or non-negative, no, positive, because we can't have 0. Plus c, okay. And then you just divide by -2 to get y by itself. Natural log, absolute value of this parabola. Okay, and then, well, we can plug in our initial condition now, huh? Our initial condition is 0, 0, right? That's the point 0, 0. Because y of 0 equals 0. That's what this is. Because it's like y of x equals the y value. Here, this is like function notation. So we get what? 0 equals -1/2 natural log absolute value of -0 squared plus 4 times 0 plus c. 0, 0, those go away. And what are we left with? When is the natural log equal to 0? Oh, and divide by this -1/2 on both sides because of the zero products property. So now, when is natural log of c equal to 0? Well, remember, log base e of c equals 0 means that e to the 0 equals what? E to the 0 equals 1. Therefore, c equals 1. So, what's our actual particular solution? Y equals -1/2 natural log absolute value -x squared plus 4x plus 1. Close that absolute value. Particular solution. And it's a particular solution because it's not a family of functions, it's just one function. Alright. Well, we can also find a particular solution curve. And the way we do that is the same thing that we were doing before. We're just finding our particular solution because it's going to be a curve. Okay. So we have slope. Find an equation of the curve that passes through 1, 3. So that's our initial condition. And has a slope of y over x squared, so that's our dy dx, that's our differential equation. At any point xy, so that's just looking for our curve. Okay. Well, we can separate our variables, so we have dy over y equals 1 over x squared dx. We can do this, where we get natural log of the absolute value of y equals x to the -1 with the negative, because this is going to be what, x to the -2, so with the power rule, we add 1 to the exponent, or we add 1 to the power and divide by the new power, and then we got that plus c. We should get y by itself, so we get, this is y equals e to the -x to the -1 plus c. And what do we get? We get, we have 1, 3. And when is that going to be? We got 3 equals e to the -1 plus c. So natural log of 3 equals -1 plus c. So c equals natural log of 3 plus 1. And the natural log of 3 is a number. So natural log of 3, natural log is being taken of 3, and then we're adding 1. So, then we need y equals e to the -x to the -1 plus c, which is natural log of 3 plus 1. And we can write that better, can't we? I think we can. Using some exponent properties, what's that? E to the -x to the -1 times e to the natural log of 3 times e to the 1. And what's that? That's 3e to the -x to the -1 plus 1. Putting these two together, busting this 3 out of logarithm jail. So homogeneous function is where this equation holds true. We'll have a definition a little bit later on. Where you have, if you plug in something called t multiplied by each variable, then you can factor out a t to the n power, where n is a number. And this is nice. It's not super nice right now in the sense that it's just like another thing to remember, but homogeneous functions are a lot easier to solve when you have higher ordered differential equations. Like, these problems get very complicated very quickly, and you're really happy during the homogeneous function section of your differential equations class. You're like slightly less happy when you're doing the non-homogeneous stuff, because you're taking the homogeneous solution and then you have to do stuff to it. So this is kind of like you're solving an equation so that you can solve other equations. This is the jumping off point, the first step. So we just need to verify that this function f of x comma y, so now we have two inputs, is a homogeneous function of degree 3, because we just plug in t of x, tx and ty. So this is the Texas and the Beanie Baby Company. So we have f of tx comma ty, and that's equal to tx squared ty minus 4tx cubed plus 3tx ty squared. And then just do some algebra. So we get what? T squared x squared ty minus 4t cubed x cubed plus 3tx t squared y squared. Further do some multiplications. We got t cubed x squared y minus 4t cubed x cubed plus 3t cubed x y squared. And now we have a greatest common factor of a t cubed, so this equals t cubed times f of x comma y. Therefore, we have a homogeneous function of degree 3. So a homogeneous differential equation is where you have m and n are homogeneous functions of the same degree, and m of x comma y dx is separate from n of x comma y dy, and that equals 0. The 0 is the homogeneous part as well. This is a key element of being a homogeneous differential equation. And these two, m and n, have to be homogeneous functions. Homogeneous functions are when you're plugging in tx and ty and you're getting out something that is a t to the nth power, and you need the same degree, so that you can leverage properties of polynomials and do stuff well. So there's that. If you're interested, go ahead and look at some differential equation stuff. So you can also have change of variables for homogeneous equations. If we have a homogeneous differential equation, then we can transform it into a differential equation by that's separable. So all the things that we've been doing are separable, where we can have dx and dy and just split them up and then solve. So we can find a separable differential equation just by substituting in y equals vx. So then we eliminate all the y's from our equation, and we just have v is a differentiable function of x. So we're just taking something that's a function and multiplying it by function of x and multiplying it by x, and that is going to be our new y. So that's fun. Alright, so in order to find our general solution of this, what do we need to do? Well, we need to make a homogeneous function. So, or we need to make a homogeneous equation with the substitution that we want. So we're going to say that that we have x squared minus v of x squared, and that's y, dy plus 3x vx dy, but then what's dy going to be? Well, remember that dy needs to come from, like, taking our derivative. And taking our derivative has to come from our original substitution, just like u substitution. Y equals vx, so dy is v times derivative of x plus derivative of v, which is dv times x. Okay, so that's dy, and we'll just substitute that in over here, where we have v dx plus dvx, and that equals 0. Oh, I put a y there, I need an x. Okay, so now we have something that we can handle a little bit more if we do some algebra. So, oh, right, did we verify that these are homogeneous? Just plug in your mind tx and ty for x's and y's here, for the x's and y's that are in there. And do we get it out t squared? I can factor out of everything? Yeah, we do, right? Okay, so let's do some algebra. We get x squared dx minus v squared x squared dx plus 3x squared v times v, so v squared dx plus 3x squared v times dvx, so that's dv and then another x, and that equals 0. Okay. And now, well, we should try to separate our variables, right? So, let's try to get all the x's together. So you got x squared, that's a factor in all of these, and a dx, sorry, that was a v. And then we have dx that's also a factor in all of those. So we have 1 minus v squared plus 3v squared dx from here, plus 3x cubed v dv, that equals 0. Okay. We're still trying to separate our variables, so let's try to move our v's over. We get, well, we can divide everything by x squared, so we just get an x there. Okay, let's try to move our v's over, so we get 1 minus v squared plus 3v squared dx equals 3x v dv. Oh, it's a negative. And now we can separate our variables. Divide by v's. So we get what? Oh, well, this should be a plus a 2v squared, combining those like terms. And so yeah, now we can separate our variables. So we get dx over negative 3x equals v dv over 1 plus 2v squared. And now, when we're trying to do this, what do? Well, I think that's going to require a little bit. On the left side, that's not so bad, right? That's negative 1/3 times x to the, oh, that's a natural log, right? Natural log of x. There's some absolute value on there. On the right-hand side, it's a little more complicated. We might need to use substitution. We have what, just use our whole denominator, right? 1 plus 2v squared, and then du is 4v dv, and then that v dv is our numerator, so we just are left with integral 1 over 4 du 1 over u, and so that gives us 1/4 natural log of absolute value of u plus c is equal to negative 1/3 natural log absolute value of x. And then, well, we can do more stuff to that. Well, we need to get that back in terms of v's, right? So we get negative 1/3 natural log of absolute value of x equals 1/4 natural log, and u was 1 plus 2v squared. Absolute value 1 plus 2v squared plus c. We don't necessarily have to solve deeper than that. Got our general solution. I guess we could flip it back into terms of x and y. So we got y equals vx. So then v is y over x. So then in this part for v, we can rewrite that. Negative 1/3 natural log absolute value of x equals 1/4 natural log absolute value 1 plus 2 y over x squared plus c. And we're looking for a general solution, so this is allowed. That was fun. Alright. Should we do more with that? I mean, I guess we could do some algebra, but it's okay. Like if you e everything up, then you can go on your merry way and find this a little bit more cleanly, but it's okay. For the sake of this video length, we're going to carry on. The answer, though, you could get x squared plus 2y squared cubed equals cx squared. Okay. So, if we know that the rate of change, the number of coyotes, is directly proportionate to 650 minus n, where t is the time in years, at time 0, population is 300, and when at time 2, so year 2, the population is increased to 500. Find the population when t is 3. So, we know that we have a directly proportional to that. So dn dt is equal to some constant, let's call it k for constant, 650 minus n of t. N is a function of t. We can separate our variables, so we have dn over 650 equals k dt, and then do our good old integration. We get, oh, this is 650 minus n, my bad. Okay. So then we get negative natural log, because of this negative right there, of absolute value 650 minus n equals kt plus c, and then we can plug in our initial condition of 0, 300. So we get negative natural log 650 minus 300 equals k times 0 plus c. What do we get? Natural log absolute value 350 equals c. Oh, hang on, I was too excited. We need to isolate a little bit more so that we can get this properly. So our initial value is got to be 350. Okay, so we need c equal to 350. Okay, So, oh yeah, okay, so we need to get n by itself. So we got natural log 650 minus n equals negative kt, and it's still plus c, e it up, so we got e to the negative kt plus e to the times e to the c, which is just c, and this equals 650 minus 650 minus n. And then we have c e to the negative k times 0 equals, oh, we're plugging in our initial condition, 650 minus 300. So then our, this goes to 1, so c equals 350. In general, our initial condition, just like when we were doing, do you remember PERT? When we were doing continuously compounding interest? Whenever we have exponential growth, the initial value needs to be what our c is. Like what we're multiplying by our principal amount. Okay, so we got c equals 350. And that's nice, I guess. We should use our other initial condition to carry on. So we have 350 going from here. 350 e to the negative kt equals 650 minus n. I guess we could do like n equals 650 minus 350 e to the negative kt, just so that we have n on its own. And then we have another point, initial condition of 2, 500 to help us solve for k. So we got 500 equals 650 minus 350 times e to the negative k times 2. And then we just solve for k. So negative 150 over negative 350 equals e to the negative k 2k. What is that? That's positive 3 over 7. So the natural log of 3/7 divided by negative 2 equals k. So then we have n equals 650 minus 350 times e to the negative, it's not negative anymore because we can just cancel it out with the denominator's negative. So we got natural log of 3 over 7 times a half times t, and then just plug in 3 there, figure out what you get. N of 3, I think, is like 552 coyotes. There's, the coyotes on the East Coast are bigger than the coyotes on the West Coast, because I think they interbreed with wolves, and so the ones over here are bigger than the ones out west. There's coyotes everywhere, though. There's coyotes in Maryland. Alright. Cool. So how about this? We got a new cereal product is introduced through an advertising campaign to a population of people, to 1 million potential customers. So we're going to say that we're using 1. We're looking at millions. The rate at which the population hears about the product is assumed to be proportional to the number of people who are not yet aware of the product. So that's dp dt is k times 1 minus proportional to the people who have not yet heard. So the entire population is 100%. If you take away, the entire population is 1 million. And if you take away the number of people who haven't heard about it yet, then that have heard about it, then you have the people who have not yet heard about it. By the end of year 1, half the population has heard of the product. How many will have heard of it by the end of 2 years? So we know that 0, 0 is a point, and we know that 1, 1/2 is also a point from our word problem. And we're looking for 2, what? So, let's separate our variables from our differential equation. dp dt equals k times 1 minus p dp over 1 minus p equals k dt. Separated our variables. Let's do the thing that we know and love. We got natural log of 1 minus p, and it's negative because of the chain rule, and that equals kt plus c. We can do some algebra, and so we get natural log, I need more coffee, 1 minus p equals negative kt plus c. E it up, so we got negative e to the negative kt times c equals 1 minus p. We got zeros, plug in 0, 0, and you get c equals 1. So that means that we have p equals 1 minus c, which is 1, e to the negative kt. Plug in our other point, so we got 1/2 equals 1 minus e to the negative k1. Negative 1/2 equals negative e to the negative k. Divide by 2, so we get natural log of 1/2 equals negative k, so k equals negative natural log of 1/2, which means that p equals 1 minus e to the negative kt, where k is natural log of 1/2 times t. So then, what are we left with? P equals p of 2 equals 1 minus e to the natural log of 1/2, and then we're doubling that. And solve that out, and I think you get something like 0.75. And what does that mean in the context of our original problem? That 0.75 million, so 750,000 people will have heard about the serial by the end of 2 years. Well, these kinds of equations are called logistic differential equations. Logistic growth is very interesting. Probably make you like do a project or a journal or something about this. But logistic growth functions are very, very applicable because exponential growth isn't really how the world works in terms of like there is a limit to what can happen, and that limit in logistic growth functions, we describe it as the carrying capacity. So if you think about like an island, even if it had like infinite resources, but it was still an island, there's a finite amount of space. So if you had, I don't know, like a population of deer that had no predators on this island, but there's still a carrying capacity for what the island can do because there's just a finite amount of space. You can't have deers like stacked on top of each other and living. So the general solution for logistic differential equations is y equals L over 1 plus b times e to the negative kt, where L is our carrying capacity. L shows up in our logistic differential equation as what we're dividing y by, as long as we have a 1 there. So sometimes this looks a little different. We have dy dt is ky directly proportional to y times 1 or L minus y. And the way that you just change this around, you just divide by L. Right? Okay. So that's logistic differential equations. This is straight from College Board of what the goal is for our class, that you can read a problem and then understand how to pull out the differential equation, from the differential equation what the carrying capacity is. The rate of change of a quantity is jointly proportionate to the size of the quantity, so that's y, and the difference between the quantity and the carrying capacity, that's A minus y, or the L minus y, carrying capacity. Alright, so how do we verify that the upper limit of y equals 4 over 1 plus 2e to the negative 3t is 4? This is a logistic growth function, where L equals 4, therefore carrying capacity is 4. Boom. Alright. This is getting kind of long, so I think I'm going to try to put this in your problem set. But writing a model for the elk population that's translating our logistic differential equation into our actual function, logistic growth function. Graphing the slope field, that means that you're drawing your little isoclines and your solution that passes through 0, 40. Use that model from 0, 40, where you have the initial population of elk is 40. And look at what happens at time equals 15. And what happens as t carries on to infinity. What's the carrying capacity? The carrying capacity is something you should be able to see just from the word problem. Alright.